Hello, everyone. In the second part, I'm going to present the hierarchical homogenization approach for estimation of effect permeability and the combination with deep learning-based surrogate model to further speed up the computing. Nowadays, the standard size of three-dimensional digital images can be up to billion voxels. Such large digital rocks make the conventional direct numerical simulation algorithms computationally intensive or even infeasible, and thus limits the applications of digital physics in practice. As shown in this figure, the computational time of conventional numerical simulation algorithms scale up with the sample size of digital rock. In this work, we aim to address this computational challenge by hierarchically decomposing the large digital rocks and using deep learning-based surrogate models to efficiently compute effective permeabilities from large digital rocks. The hierarchical approach consists of 4 steps. At first, we divide the large binary segmented digital rock at the macro scale into a set of subvolumes. Then we rapidly predict the permeability of each subvolume at the macro scale using a convolutional neural network with transfer learning. Then we sample the upscaled rock model by assigning the predicted permeabilities of subvolumes to the corresponding cells. It results in a heterogeneous permeability field at an intermediate scale. Finally, we compute the effective permeability at the macro scale by solving Darcy equations on the upscaled rock model. Clearly, the subvolume size is a key factor that affects the numerical errors induced by the hierarchical approach. To determine the subvolume size, we investigate the effect of subvolume size on numerical errors using 2 Sandstone samples and 2 Carbonate samples. As we can see from this figure, for the 2 Sandstones, the relative errors clearly decrease as the subvolume size increases. Since the 2 Sandstones are highly heterogeneous and have low porosity, some subvolumes with too small size are not large enough to capture local microstructures, thereby leading to large numerical errors. For the 2 raw carbonate samples with high porosity and the relation between the relative error and the subvolume size is not very clear, but the relative errors with almost all subvolume size remain less than 5%. In this study, the subvolume size of the training samples is set to 200 by 200 by 200. That is sufficiently large to capture local microstructures of most digital images and to guarantee small numerical errors induced by the hierarchical decomposition. Also, such subvolume size allows us to generate sufficient training samples with permeability obtained through direct numerical simulation. That is very important for the training of the CNN surrogate model. As illustrated in this figure, the surrogate model is a 3D convolutional neural network, which is modified from the VGGNet. The network includes two components, a feature extractor and a regressor. The feature extractor consists of 6 convolutional blocks which extract the salient feature representation that is most sensitive to the permeability. While the regressor consists of several fully connected layers aiming to predict predicted permeability from the extracted feature maps. In the inference stage, we freeze the feature extractor of the pre-trained CNN surrogate model and just fine-tune the regressor using a small number of labeled data from new digital samples. This procedure is referred to as transfer learning. Considering that microstructures of porous medium vary with rock types, we train different surrogate models for Sandstone and Carbonate with 2 sets of micro-CT data. In this slide, we show the Sandstone rock samples. And in this slide, we show the Carbonate samples. Here we show the prediction accuracy of the CNN surrogate models. We can see that the predicted permeability of subvolumes in the validation set by the CNN surrogate models are consistent with the result obtained from direct numerical simulation for both Sandstone and Carbonates. The R2 score are up to 0.99 and 0.95 respectively. One potential issue existing in data-driven methods is the capacity of generalization. The pre-trained models can lead to inaccurate prediction, in particular for samples that are significantly different with those in the training set. From our experiments, when applying to new rock samples, the predicted permeabilities of subvolumes by the pre-trained CNN surrogate models are sometimes clearly biased with respect to the result by direct numerical simulation. To make the CNN surrogate models robust to new digital rock samples, we propose to fine-tune the last fully connected layers using a few labeled data before predicting permeabilities of the whole set of subvolumes. As mentioned before, this procedure is referred to as transfer learning. For the transfer learning of the pre-trained CNN, we select 10% or to 20% of the subvolumes and compute their permeabilities using the LIR solver of the GeoDict software. And we can see that the predicted permeabilities of the subvolumes by the CNN surrogate models with transfer learning are consistent with the ground truth obtained by the LIR solver. Once we obtain the permeabilities of subvolumes, we can assemble the upscaled rock model and compute the effective permeability of the full rock volume by solving the Darcy equations at the immediate scale. Here we compare the predicted effective permeabilities of the full micro-CT volumes by 4 different approaches. Direct numerical simulation on the full large digital rock, hierarchical method with DNS to get the permeabilities of subvolumes, hierarchical method with CNN to predict permeabilities of subvolumes, and hierarchical method with cosmic commands to predict permeabilities. As we can see in this figure, the effective permeabilities predicted by the hierarchical method with CNN are close to the values by the hierarchical method with DNS for all the rock samples. And it also has a good agreement with the results obtained by the full DNS. All effective permeabilities predicted by the full DNS fall in the 1 standard deviation interval of the hierarchical method with CNN surrogate model. The main advantage of the proposed hierarchical approach is that it provides a computationally efficient way for rapid estimation of permeability from large ditch rocks by slightly sacrificing the prediction accuracy. The computation time of the hierarchical method with DNS is slightly reduced for the Market Sandstone and the Benthamer Sandstone, while reduced by over 2 times for other samples. And our proposed hierarchical method with CNN surrogate model can further reduce the computational time from hours to minutes using 1 GPU. The speed up ratio ranges from 5 to 13, depending on the complexity of pore structures. Okay, thank you.